So far we have been discussing extensively the case of the anomaly generated by a fermion in an arbitrary representation, a complex fermion. But as probably most of you know, you can have other kinds of anomalies, other fields in your theory, or more generally, other ambiguities in the phase of the partition function. The general picture doesn't change, so you always have your free theory here in the dimensions, and to fix the phase of the partition function, you want to attach it to some theory in one dimension higher, whose partition function defines the phase of the partition function that you're interested in. So this theory in one dimension higher is known as the anomaly theory. A different way of saying this that may be more familiar for certain people in the audience is that we are doing some version of anomaly inflow here. We want to view the anomaly as coming from some bulk. But it's useful to think of the theory on the bulk as some theory in itself. In this case, a very easy one, SPT, but in this lecture and the next, we will start generalizing this to non-invertible theories. And this doesn't have to be the eta invariant. So an example that we have studied so far was the anomaly theory, if you like the action for the anomaly theory. Was 2 pi I times the eta invariant of the Dirac operator. This does not need to be the only thing that you can consider. Another example, which I think was covered in Thomas's lectures. You can have some anomaly theory for Maxwell, which was the background for the electric one-form symmetry, which D of the background for the magnetic symmetry. I don't know which notation exactly he used, but he wrote an anomaly theory like this. Today I'm going to describe some other examples of anomalies that can arise in string theory. String theory has fermions, but it also has other fields that contribute. So I'm going to discuss those. My discussion will be a little bit restricted because I want to get to the SymTFTs at some point this week. And the study of the global anomalies will be fairly technical. It's, as you saw in the case of the fermion, we could compute the eta invariant, but it requires some work, computing Bordism groups and so on. So if you check my lecture notes in the webpage, you will see references to papers that do this exercise for, well, not exercise, but these interesting computations for string theory. I'm going to deal with the local anomaly today. So I'm going to compute the local anomaly for type 2b string theory and type 1 string theory. And I'm going to show that at least these two vanish, and this was already a very important result at the time. Of course, you still have to check global anomalies, and that was something that, in fact, is still ongoing work. So there's recent papers from the last few years that are still verifying different examples of string theory and making sure they don't have global anomalies. So this can get quite involved. All right, let me start with one of the simplest cases where you have something interesting going on. Type 2b string theory. How many of you know what this means, roughly? To see how much I need to review. Okay. Great. So I guess some subset of you that know what this means will have thought of this in terms of the worksheet. There's some specific worksheet that gives you some particular string theory. But my viewpoint in these lectures is going to be the target space picture. So for me, this means really going to work at low energies and think out the type to be supergravity. Of course, there's something to be said about the worksheet, but this is the step 0 of the computation, making sure the supergravity makes sense. And the type to be supergravity is not very complicated. So what do we have? We have a graviton, antisymmetric two-form, and a scalar. This is known as the dilaton. There's also some fermions. Well, let me stay with the boson. So these are all bosonic fields. The graviton obviously is, and this is a boson, another boson. There are some more bosons in the theory. There's some antisymmetric forms. C0 is a periodic scalar. There's also a C mu nu. And the star of the show today will be the next one, C mu nu rho sigma. So this is an antisymmetric two-form, which is closely related to this one. And this one here is an antisymmetric four-form connection. Subject to a constraint. And the constraint is that you take D of this C, I'm going to call it C4. You get a star of D of C4. So it's consistent when you're talking about four forms in 10 dimensions to impose that their field strength is self-dual. This is an irreducible representation of the Lorentz group in 10 dimensions. So this is one of the things that will make life interesting for us, but thankfully the fact that it's interesting enough will save the theory, will make the theory consistent. We also have some fermions. So we have something which is a gravitino. Let me show the conventions are the ones I want. Yeah. So we have a gravitino. This is a field that you can model. There are some subtleties. It's a fermionic field which has one spinor index and one vector index. And I'm going to view this as a Weyl gravitino. In 10 dimensions, this is not the minimal choice. I could impose additionally Majorana conditions, so there's such a thing as Majorana-Weyl fermions in 10 dimensions. So this theory is typically known, if you count Majorana-Weyl fermions, as the n equal to 2, 0 theory. That's because you get two Majorana-Weyl gravitinos of the same chirality. Okay, but I'm going to think of this as a Weyl gravitino. And finally, we get some extra field here. I'm going to call it lambda, I think. No, I'm going to go upside. Which is a Weyl spinor of negative chirality. So the dots here are a convention that's widely used in supergravity to keep track of the chirality of the spinors. If you see a dot, it means negative chirality. Okay. So the only thing here that doesn't require any thought at all is this Weyl spinor of negative chirality. We know how to deal with fermions, and know how to write the local anomaly. That's a hat times the Chern character. This Weyl spinor is neutral under the gauge group. There's no gauge group here, so it's just the a hat. So this one we know how to compute the anomaly theory for. So the index density, I should say. But some of the other fields require some thought. These fields here, these are bosons, and they can be regulated in a way that doesn't break any of the symmetries that we're after, in this case, Lorentz invariance. So we don't need to worry about this further. The same is true for these two. But this one is going to be subtle. There's going to be an anomaly coming from this one. So this one I will have to discuss in detail. I will do that in a second. And the Weil gravitino is also something I haven't explained so far. It's a fermion, yes, but it transforms under the tangent bundle, not as a spinor, but as a spinor times vector. So I'll have to deal with that. So let me start with the gravitino. Luckily, much of the work I have done so far can be recycled here. I won't have to spend a lot of time discussing this case. The basic idea is that I'm going to think of this as a fermion, which is a spinor, which is coupled to a gauge bundle, my E, which happens to be a tangent bundle. And it couples in the vector representation of the tangent bundle. So think of the gravitino as a Weil fermion coupled to the tangent bundle. And by this, what I mean precisely is in my formulas, I'm going to choose E. So remember that my I for a fermion was A hat tangent bundle of my manifold times Chern character of E. E is going to be the tangent bundle in the vector representation. Okay. So I can almost write the correct formula thinking in this way. So I want to write the index density, the thing that's going to give me the curvature of the terminal line bundle for a gravitino. But there's a subtlety here that I'm going to discuss in a second. So this is the wrong formula. I'm going to fix it in a second, of course. But this is my first approximation to a formula, which is going to be A hat tangent bundle of my manifold M, some 12-dimensional manifold, times the Chern character of E. Remember the Chern character here was trace of E to the I F divided by 2 pi. If I'm coupling to the tangent bundle, my F is as R, the curvature 2 form. So this is E trace of E to the I R divided by 2 pi. So this is almost correct. There's a subtlety though, and the subtlety comes from the fact that supergravity in any dimension is a gauge theory, where some of the gauge transformations are fermionic. That means in practice that some of the degrees of freedom of the gravitino are going to be gauged away and do not contribute to the anomaly. There's a simple way of taking this into account. So the idea is the following. The physical gravitino is going to be a spin 3/2 particle. Sorry, my notation is not great, is it? Yeah. It's going to lead to a spin 3/2 particle after gauge fixing. And this is the actual degree of freedom that leads to anomaly, the spin 3 half particle. But the tensor product of a vector and a spinor is not a spin 3 half particle in general. Vector times a spinor is spin 3 halves, so it's spinor of 1 half, plus a spin 1 half. This is the basic fact. This is not entirely unfamiliar, hopefully. If you think about the Klebs-Gordon way of taking products in SU2, you take a spin 1 times a spin 1 half, you get a spin 3 halves plus a spin 1 half. This is what the formula means. It's just Klebs-Gordon. What this gauge fixing is doing, what the fermionic gauge transformations are doing, are removing this spin degree of freedom. So this one is removed by gauge transformations. Okay, so I have to take this into account. The anomaly is not going to come from the fundamental field or only from the degrees that remain after gauge fixing. Or alternatively, you can do quantization in terms of costs and include anomaly due to the costs. Either way, what I need to do is to subtract the contribution of a spin 1 half fermion from this anomaly. So we know what that is. Now that this is the right formula. I subtract the contribution from a single fermion, which is AM. So this is typically written as AM TM, trace of e to the r divided by 2 pi minus 1. Okay, so that's the anomaly of gravity now. Any questions? So obviously this is a little bit heuristic. It will take me way too long to do the proper quantization, but I can give you references. I can write that. New when who is it? Okay, so this is one paper where things are done carefully. Oh, so 81. So this is a paper where things are done carefully. Yeah.
So is there a way to do it without gauge fixing?
Yeah, you can do the deformation in terms of the field and the ghosts and anti-ghosts if you want. It's sort of gauge fixing, yes, but that allows you to see this contribution, the minus here, as a contribution of a ghost. Or more precisely, you have two ghosts of negative chirality and one anti-ghost of positive chirality, I think it is, and they cancel with each other, so it's a little bit subtle.
Isn't the most interesting piece the overall coefficient, no? Like how much the anomaly is actually equal to?
Even this one here?
Like the overall coefficient of how much a gravitino gives. The famous 496.
Ah, yeah.
That's the most interesting piece, no?
Yes, well, that comes from expanding this and going to 10 dimensions or 12 dimensions. Yeah, I'm going to write the proper formulas with coefficients later, yeah. This is the general formula, but of course you have to pick pieces depending on dimension. Yeah. Any other questions?
So does similar consideration holds for higher spin particles, or you can always start by doing the naive thing and then use the SU2 representation to remove the...
Yeah. In fact, there was a very nice talk yesterday in the context of the 4,0 theory where a similar sort of calculation was presented. Yeah.
So you're somehow gauging the supersymmetry, not just the diffeomorphism? Is that how I should think about it?
Yeah, I think that's the right way of thinking about it. You're working on supergravity, and you're gauging something which is a fermionic symmetry generated by a spinor. That's going to weight away basically a spin 1/2 particle away.
But wouldn't be that true also without supersymmetry, no? You just have spin 3/2 particles, and that would be true without supersymmetry. Because spin 3/2 particle is irreducible.
Yeah. Mm-hmm. I guess the thing I'm saying is, yeah, if I try to write my supergravity Lagrangian in terms of these fields, it's not quite the theory of a spin 3/2 particle. To say this is the theory of a spin 3/2 particle, I have to take into account the supergravity transformations that kill some of the degrees of freedom. If I had a different way of writing the theory of a spin 3/2 particle, not as a vector times a spinor, then I wouldn't have to worry about this subtlety indeed. Yeah.
Wait, are you saying that the spin 3/2 particle is not the same as what Schwinger wrote in the 50s? Rarita Schwinger particle? I mean, it was way before supersymmetry. People, wrote the Lagrangian for spin 3/2 particles.
Yeah.
They all have the same gauge invariance that removes the spin 1/2 component.
Yeah, that's correct, yes. Yeah.
You just want to call supersymmetry.
Yeah, I'm not saying anything other than that, yeah. This gauge invariant removes this degree of freedom, that's what I'm saying. Yeah.
Sorry, this is a naive question, but can you please repeat why the psi alpha dot doesn't contribute to the anomaly?
No, sorry. I hope I didn't say that because that's not true. The thing that I said is that I'm not going to worry too much about this today because I know what this does. This while spin of negative chirality, and my last two lectures have been basically talking about this kind of objects. I know what the anomaly theory is for this one. It's going to be minus A roof genus.
So a very basic question, but is there some theorem that states that gravitinos cannot have any gauge charge, or can they not contribute to gauge?
Yeah, that's a good question. So it's not difficult to generalize this to gravitinos which are charged under some other symmetry. You get a coupling here with some E, which is the now internal symmetry you're talking about. This doesn't happen to be, and I know the reason why I should discard this, but I don't know any theory where this happens. Yeah. Okay, any other questions? All right, so we took care of most things in there except the self-dual field. So let's take that. Let's think about that. All right, let's do it. Okay. Should be able to see everything now. So the self-dual field. And we use a similar trick. So a self-dual field can be obtained. Well, first of all, these are complex representations. When you are in 40 plus 2 dimensions, which is the case for us. So in principle, they can give contributions to anomaly. This is one of the reasons that we cannot forget about them. And a sort of quick way of understanding the answer I'm going to give you is thinking in the same way as I did before. In the tensor product of a spinor times a spinor. So if you do a spinor times a spinor, you get something like vector plus 3 index antisymmetric plus self-dual 5. This is for D equal to 2.
Are they complex presentations in Euclidean or Lorentzian symmetry?
I'm thinking Euclidean here. Okay, so this is not quite the same as before, but it's related. I get the object I want, the self-dual 5 form, and then two representations which are real. These ones in this case are not going to contribute to the anomaly. So I can understand the anomaly of self-dual 5 form by studying the anomaly of a particle with two spinor indices. I'm not saying that they are the same particle. I'm not saying that, like in the previous case, they're related by case transformations. What I'm saying is that the anomaly polynomial will behave as if I can forget about these two contributions. So I'm just going to write the answer here. Hopefully this is enough motivation. But there are a couple of factors I cannot justify without going through a long calculation, or at least I don't know an intuitive way of doing that. So I'll give you a couple of references where you can verify those. So this is -1/8. A roof of trace of M. And then, in this case, E is the spinor bundle, not the vector bundle. So the tangent bundle in the spinor representation. So what I need to do is write the generators of the field strength in the spinor representation. And it can be written in this way, with the gamma matrices as usual. Okay, so this part is relatively easy to understand. Just this intuition here. The factor of -1 here is because these are bosons. So they contribute negatively to the determinant. So what I mean is this goes in the exponent, so this is 1 over the determinant as usual. The factor of 1/8 is trickier. There's two ways of arguing this, and I think the best way probably is trying to work out some Feynman rules and compute the diagrams. That's what Albert Gaumet and Witten did. Now, this calculation was perfectly correct, and the ideas that they used were correct. But it's sort of made more difficult by the fact that it's very difficult to write Lagrangians for self-dual forms in 10 dimensions. The basic abstraction is typically when you want to write the kinetic term for some object, you write something like this, with this the field strength. So this will be this of C4. But because we are saying that d of C4 is equal to a star of d of C4, this is dC4 which dC4. This is odd degree, and you get 0. So the most naive thing that you can do, you cannot do. I mean, you get 0. You don't get the kinetic term. You have to think a little bit harder. Of course, since then, people have proposed many Lagrangians for self-dual forms. And you can reproduce these factors through some more complicated formalism. So here's a reference in case you're curious. So I'm going to leave this a little bit mysterious. I'm not going to say much about this factor of 1/8, just because it's not so straightforward. That's the correct answer. All right. This admits a nice rewriting to something that's more familiar, at least mathematically. This can be written as 1/8 L, where this is the Hirzebruch genus. So remember that this was some polynomial in R. This is some polynomial in R. As you expand, you will notice that this coincides precisely with mathematicians called the Hirzebruch genus. So this formulation is much easier to compare with literature and so on. Okay, so now I have all the ingredients that I need for verifying that type 2B is anomaly free. So let me put the factors in front that Sohar was asking about. These are so this is the anomaly, so the index density in 12 dimensions for a spin 1/2 fermion. The numbers here are something you can compute by doing the expansions of the error of genus and so on. They are not particularly transparent, but you can obtain them. By the way, everything I say now, you can do the exercise. This is not an exercise I wanted to put for the exercise session. It's a long exercise. But if you have one day you want to spend on this, it's a good way of making sure you understand these things. Yeah? Okay, so that's the contribution of a fermion written in terms of the Pontryagin classes. All I'm worrying about here is the gravitational anomaly, so all I have is R, so everything will be expanded in terms of Pontryagin classes. This happens to be the, I think, neater way of thinking of these things. Then we have a contribution from the gravitino, or the spin 3/2 particle. I'm going to keep the coefficient the same in all cases. So in fact, these expressions are just taken from the paper by Luis Albergamé and Witten. There's ways of simplifying some coefficients sometimes. And here's finally the contribution from the anti-self-dual form. Self-duals, let's say. So this is 12. All right. So hopefully I didn't make any typo. The coefficients are supposed to be all the same. So if they differ, that's a typo. Take the majority rule. And the rest is hopefully correct. The reason I wrote this in some detail.
Probably there should be a plus sign on best first. In front of 44. The first.
Let's see. You think this is a minus? Yeah. Why do you think it's a minus?
I'm hoping that it was not to 0.
Okay. Oh, I see why you say that. Sorry. Yes. My convention is that this is for a positive chirality spinor.
Okay, cool. Okay.
And I'm taking this to be a negative chirality spinor, so the minus is going to come from there. Yeah. Good catch. Yeah. Very good. Okay, yeah, so many of you are doing the exercise in your heads. Do these things adapt to 0? Let's think if they should adapt to 0 in general, if these numbers were random numbers. You want to cancel each coefficient individually, as you want to do. And if you think of these coefficients as a 3 times 3 matrix, what you're asking is that this matrix has a kernel which is non-zero. A generic 3 times 3 matrix will not have a non-zero kernel. It is generically there will not be a combination of these things that satisfies the anomaly cancellation conditions. One of the magic things that happens is that indeed, in this case, the anomaly cancellation conditions are satisfied. So assuming we have ni of each type, a solution is n1/2 equal to -1, n3/2 equal to 1, and ns equal to 1. And this is, of course, the content of type 2B supergravity. Interestingly, this is sort of the only solution up to rescalings. And the fact that I have one bile gravitino here means that if I, for physical reasons, don't want to have more than 2 Majorana-Weil gravitinos, that gives rise to 2 big representations. This is the only solution that you can construct.
Nick, I had some, maybe I didn't know this before. The anomaly I doesn't have to be an integral formed. I would think it has to be an integral form by anomaly inflow arguments.
Yeah.
And this 1/8 is therefore offensive.
Yeah, it can look offensive, but for example, you think in 4 dimensions. The signature on a spin manifold is always a multiple of 16, so you can have congruences.
Okay. So this means that the anomaly really cancels on some subclass of the manifolds, which are spin, and that's enough?
Here I'm checking the local cancellation of the anomaly. For that, I need this to cancel locally as a form.
Right, but on which manifolds is it even an integer form?
Well, it's possible you have an integer form. Think of a fermion, a spin 1/2 fermion. Right, the anomaly is a hat. That's going to give you some integer if you integrate on a 6 manifold, which is a spin, because that's what spin means, that's the index. But it doesn't have to cancel locally as a form, even if it's integrally quantized. So I want this determinant line bundle to have 0 curvature. And that's something I can do in a neighborhood of a point. I don't need to
the 1/8 times L, on which manifold is it even defined? Because of the 1/8.
I mean, there's different questions here, I think. Let me make sure I answer the one that you're asking. If I apply the index theorem to the signature complex, the thing that appears is just L. L will also have some factors of fractions in front of the p's, like a roof does. Those factors will always imply not that this is not well defined or as a number or anything like that, as an integer. It means that P1 square, or whatever combination you have, integrated over the manifold gives you a multiple of the prefactor, so you get an integer. Yeah. So that's one thing. In this case, I'm not computing the index literally in 2 dimensions higher. I'm saying that the anomaly, the local curvature of this bundle, is related to the index of a self-dual form by this factor of 1/8.
Okay. So this is not the global form of the anomaly. This is just the local form of the anomaly.
That's correct.
So there is no 1/8 in the global answer.
Well, that's interesting, in fact.
Okay.
So if you want to answer that question, that's related to the global anomalies of type 2b. Okay. What you want to do in that case is go kind of one level lower to anomaly theory, data invariance I've been talking about. And there you have the question thing you're hinting at, which is that you have the eta invariant of one of these forms divided by 8. And that's not apparent that will give something consistent and enclose manifolds. And it's analogous to the questions like in M theory, you also get this 1/6 over C3 times C3 G4 G4. So then what will happen is there are congruences. The eta from here and the etas from there will conspire in such a way that it doesn't, that's way beyond what I'm going to explain today, but yes, that's something you need to worry about, but only for global anomalies, which is not. Thank you. Yeah. Other questions?
Just double check. Is that 1/8 factor appears in any dimension you are analyzing?
This is dimension independent. I think, yeah. Mm-hmm. I believe so. Okay, any other questions? Okay, so when Luis Albert Game and Witten wrote this paper, they were, of course, perfectly well aware that type 2b is not the only string theory. There are others. There was type 2a at the time, which is a non-chiral theory, so for one, there's not much of an issue. There's really not much to check. But you also have type 1 string theory. They had type 1 string theory at the time. And if you actually do this calculation for type 1 string theory, you are going to get a non-zero anomaly polynomial. So let me sketch what happens in that theory. So let me do anomaly cancellation. In type 1 or heterotic. And again, some of you might know what this is in terms of the worksheet, but I'm going to think of this as a supergravity. Okay. So as a supergravity, this is, in this case, 1, 0. So the gravitino is going to be Majorana by in this case, which is 5. And the fields, okay, so you still have the metric, you still have the two form, and you still have the dilaton. These don't change, but they don't enter the anomaly, so it doesn't matter. You're going to have a gravitino, but in this case, this is going to be Majorana bile. There's a dilatino, as before. Okay. I think at this point in my notes, I regained my sanity and I called the dilatino something different from the gravitino. So it's going to be chi now. So this is the dilatino. And again, this is of opposite chirality. And the new ingredient is that in type 1, you can have supergravity. So a Yammer's theory. So you have an A mu and a lambda with positive chirality. So this is a gauge boson. And here I have a gauge gene. Okay. If you don't know supersymmetry, which I might, some of you coming from condensed matter might not be, might not be your day-to-day thing. Just think of this as a gauge boson for a gauge group and a fermion which is charged in the adjoint representation of that same gauge group. So there are certainly some similarities. I don't have, in this case, to worry about the self-dual field. There's no self-dual field. I have a dilatino, and I have a gravitino, and I have a gaugino, which is just a fermion. So here I have already done enough that I can just expand the contributions, right? So this one I brought before. This is going to be 1/2 because it's Majorana. A roof trace of e to the r over 2 pi minus 1. So I can just write it down from what I know already. Dilatino is, as before, just a fermion with opposite chirality. This is going to be minus a roof genus. And the gauge genus are interesting. These are positive chirality, so a roof genus, and then these are charged in the adjoint representation of the group. So this is going to be trace in the adjoint representation of e to the I f over 2 pi. Okay. So this is the local anomaly. Once you have enough technology, these things are relatively easy. And again, I encourage you to work through details. I'm just going to give you a final answer. So the final anomaly polynomial is the following. So adding up all those contributions, I get something like the following. Dimension of G minus 4 and 6. P3. Oh, that's it. Up to order factors that don't matter too much, times P3 plus some number trace in the joint of F cubed. Okay, so there's a complicated expression you can write down. I don't need to explain to you what it is. If you want to do it, I encourage you to do it. And the full formulas are in some of the references I wrote in my lecture notes. The thing I want to highlight is once you do the calculation, you don't get 0. That's the important thing. That led Albert Gaume and Witten to say that this theory had a gravitational anomaly. A few years later, Green and Schwartz realized that there's a way of cancelling this anomaly, make this theory consistent, in a rather interesting way. So Green and Schwartz proposed the following. So I said, well, let me pick G. So this will only work for some choices of G. These are very special choices, such that I12 factors as two pieces, x4 and x8. So can we do this? Well, according to what I wrote there, this requires that the dimension of my group is 496. This term definitely does not factor. P3 does not factor into pieces. So if I want to cancel this, the only thing I can do is kill this prefactor. Luckily, there are groups where this happens. But I also want that the trace of the joint factors, that's an F6, of course. There's a 12 form. I want this term to factor also. So I want the trace in the joint of whichever group I have of F6 to factor, so up to constants perhaps, into trace in the joint of F4, trace in the joint of F2, and F4. I could consider the factorizations, but this is the one that's going to matter. Okay, so this seems like a very strong constraint. But in fact, it's satisfied by a number of groups, 4 exactly. Okay, so here's a little group theory exercise for you. Verify that the dimension of these groups is always 496, assuming I didn't make any typos, and that this factorization property happens. So this is an exercise. Okay, so, yeah, in these expressions, X4 is some characteristic class. Depending on R and F. And as it happens in string theory, X4 is trace R square minus trace F square. So what am I doing here? I'm writing the whole anomaly polynomial and specializing it to those groups there. And I'm seeing that it factors, and the way it factors is with a prefactor, which is of order 4 of this type, times x8, which is a more complicated expression. All right. So define omega Chern-Simons of R, I'm going to say, such that, as usual, this is trace R squared. So Chern-Simons form for gravity, and the same thing for F. So this is trace F squared. Okay. So far this is a numerical coincidence, and whenever I have a characteristic form of that type, I can always write these Chern-Simons terms. And didn't do anything really to the theory so far, apart from specializing some examples. But now I'm going to change the theory. I'm going to modify B such that BB minus omega Chern-Simons R minus omega Chern-Simons F is gauge invariant. So does this mean the Chern-Simons forms are generally not gauge invariant? They change by total derivative, as you know, by descent. So there will be a total derivative of something, and I say that every time I do a gauge transformation in the Lorentz bundle or in the gauge bundle, I change F accordingly. This is not the standard transformation of a two-form that we are familiar with. I'm changing the nature of this two-form. Whenever I'm gluing patches, I'm going to change F in a way that's not very natural from the standard definition. But I can do that. Okay, so now I have changed the nature of my B field. So this is step 1. This is 2, and step 3. I add the coupling B2 wedge X8 to my supergravity action. Okay. If the word add here bothers anybody, please hold your complaints for a second. Come to that point immediately. But let me explain first why this fixes the problem for you. So what's going to happen? This B is not going to be gauge invariant under transformations of R or F of the Lorentz or gauge bundles. It's going to transform precisely as the anomaly encoded by the descent by the Chern-Simons term. So the gauge transformation of this term is precisely going to cancel the anomaly that I get from the rest of the theory. It's constructed in such a way that this thing changes precisely by gauge parameter times anomaly. So this fixes the problem. And in fact, the thing that was amazing and got people very excited at the time was that this coupling did not have to be added. It arises in the supergravity by itself. So it always had to be in the theory. So they computed some string loop diagrams and so on, and they saw that these two terms were already indeed appearing in the couplings of B. So string theory through this coupling was found to be consistent. Now, when I learned these things, I always thought that this was a really magical thing that was very special. As I got older, I hesitate to be wiser, but older and more jaded, I realized that there's other examples that work in very similar ways. So if you have, for example, a similar example, maybe to demystify this mechanism a little bit, you have some U1 symmetry times some other U1 symmetry, so it's A and B, and you do with a mixed anomaly. And you do a gauge transform of A, say. You might get that the action of your theory goes to the action plus the gauge parameter times f of b squared. Right? You mean that the anomaly is fa fb squared. That's what you're going to get. That's an anomaly. I can cancel this. By introducing a new field theta, coupling as theta b squared, so like an action, with transformation theta goes to theta minus lambda. Okay. So this is something that's very familiar. If you have ever done cyberecology, for example, for n=1 theories, very often when you have an anomalous U1, you introduce an spurion field and you make it transform in such a way that you restore the symmetry which is anomalous.
By this token, you can cancel any anomaly, not just those that look like products.
Yeah, I can cancel U1s at least. Yeah.
No, any anomaly whatsoever. Take any anomaly, any variation of any action, and some deformed field, and you can shift it away.
Yeah.
That's called an axion. That's an
Yeah,
axion.
it's an axion.
With an axion, you can cancel any anomaly that you want.
Sure.
The Green-Schwarz mechanism is only about very special situations where it's a product.
Yeah. This case is a product, right?
No, in this logic, you can cancel any anomaly whatsoever. Just add to the action an integral of a field, and let that field transform by the anomaly.
Yeah.
And that's it.
Okay, maybe it's not a very good anomaly. A very good analogy, yes. This is an example. I just wanted to illustrate an example where things factor and you have something similar. Yeah. But you are right that this is more special.
I guess the interesting thing is that the coupling arises automatically there and you don't have to add it yourself.
Yeah. Yeah, that's something that could have spoiled this argument, right? You could have said that this could happen to fix string theory, but then the coupling had to be there. And the computation, you do it and it's actually there. Yeah.
So can we reformulate this in the language of two groups?
Yeah, this is very close to that. Yeah.
Right, but it's clearly very close. But can I actually make it like a gauge two group? Or it's actually different in some of the details?
Not as far as I know, no. If I think of this B as you say, as a gauge 2 group whose transformation involves the gauge parameter of F, that's the standard definition of a gauge 2 group, as far as I know. Yeah. Okay, very good. Any other questions?
There's some 2 group that involve Lorentz symmetry.
Yeah, that's the part that was giving me a bit of pause. Yeah. Yeah. Okay. I think I'm going to stop here. There's of course much more to say, but I want to say something modern because this school is called Modern Technologies, and this thing is very old. But I think it was hopefully interesting. No, that doesn't work. So I think one thing that I omitted, which was important, was global anomalies. I did some discussion of global anomalies in field theory for this U2 theory. And you can do very similar analysis for string theory. It's much more complicated technically, but you can. So there's a number of interesting papers that appeared, as I mentioned before, in recent years, and they're all in the lecture notes. If this was something you're interested in, I recommend that you read those papers. They're really quite good. Right. So today and tomorrow I want to talk about SymTFTs. Yeah.
So can you say a bit more about when you're allowed to change the gauge transformation of something like B? Like, why are you allowed to do this, change in the gauge transformation?
It's a hard question to answer, I think. One thing I think I can answer is, does this make sense as a global object? Meaning, can I construct some model of something that generalizes differential cohomology, for example, that incorporates this shift? And that's done. There's, for example, a paper of Fried I can tell you later. They will explain in which sense this B. They will explain what this B is. They will explain what this B is. Now that's just a proof that this thing makes mathematical sense, at least in the framework. You can show that there's an object that behaves like that B. Same when things are inconsistent is more difficult for me because. Let me give you something that puzzles me out the whole business that I don't know how to answer. In type 2B string theory, there's SL2C that relates the Neo-Schwarz and Ramon sectors. A good way of thinking of this B involves something known as K-theory. Or at least it enters in some modified version of K-theory in the theory. So it's H-twisted K-theory. But we don't have a formulation that glues these two points of view together. So we don't have a good SL2C invariant, well, good or bad, we have an SL2C invariant formulation of K-theory for type 2. I think most of us believe that that's not a problem with the theory, it's just that we are not good enough at formulating it mathematically. But if I were to do a mechanism like this seriously in type 1, which is a version of type 2 which has an oriented fault, I'll probably have to use these ideas if I'm going deep enough. So, sorry, everything I'm saying is in some sense a long version of I don't know what the full constraints are for this mechanism to make sense globally. Yeah.
Is there an SL2Z invariant formulation of differential cohomology, which is a more tame version of that?
Yeah. Yeah, my answer was about H-twisted differential cohomology. In the H-twisted version, H behaves very differently from the thing that you're twisting. So that was the issue.
Your analogy with the axion. So the axion in particle physics appears when there is spontaneous breaking.
Yeah.
So is there some sense that people understood that maybe string theory is in some spontaneously broken phase?
Yeah, I would love to be that extremely precise. So I have a paper with Nabil Iqbal, where we try to use, so there's an issue, which is that you don't have symmetries in string theory, so you don't know what's being spontaneously broken. Even if you sort of forget about that, think of the low energy supergravity, you have Chern-Simons terms that break those symmetries in some way. But you can think about constructed generators that are basically the non-invertible symmetry generators that do that. And locally, at least, they seem to behave nicely enough that you can construct some sort of Goldstone theorem for those. And those explain some of these, the Raman fields and the NS fields in that.
It's not related to the Higgs mechanism of Shatashvili in the string field theory?
Oh, that I don't have.
Okay.
Thank you. No, I'll look at it. Yeah, but my intuition is that I think of these fields as Goldstone fields. But the question is Goldstones of what? Because there are no symmetries in string theory. Yeah. Any other questions? All right. So let me do something a bit less classical. I want to understand symmetries and anomalies from string theory. So in sense, everything I have said so far are trying to understand the symmetries, of which we believe they're none, and anomalies, of which now I sort of half convinced you that there are none, of string theory. But now I want to understand symmetries and anomalies of field theories using string theory techniques. So now string theory is not going to be my target. It's going to be a tool for understanding symmetries of anomalies of quantum field theory. And I should say that everything I said so far, much of it at least can be done very precisely. In what I'm going to describe now, this is much newer and lots of open questions. I'm going to tell you some of the things I understand, but you'll see soon that even elementary questions are still a bit murky. So during the panel, somebody was asking about good problems. That depends on your interest, of course, but there are definitely problems here. But I think, I should say, not problems that we believe this might eventually be inconsistent. We know this is going to work, but how it works in detail, that we don't know. Okay, so for concreteness, I will focus on a specific theory, and that's going to be n equal to 1 super-Yang-Mills in 7 dimensions. This might seem a bit funny, but this is sort of the simplest example I know of these things. With gauge algebra SUN. So this is a theory that has interesting generalized symmetries. These generalized symmetries have anomalies, and this is a theory that has a relatively simple string theory engineering. So my task is going to be reproduce what we know about field theory from the string theory construction. Okay. I'm going to make some statements, and I would like to know how familiar they are, to know how deeply I have to go into them. So this theory, if I choose the global form of the gauge group G to be SUN as a group now, that was an algebra, this is a group, has a one-form symmetry, set n, measuring Wilson lines. The fundamental. Is this familiar to everybody? Or is it unfamiliar for anybody? Okay, very good. So I will not explain this. Notation I will call backgrounds for the symmetry. Bit. Okay. For global form SUM mod Seden, this theory has a symmetry, which in this case is a 4-form symmetry. Measurement of lines and backgrounds will be C4, C5.
The lines is a misnomer, right?
Yes, indeed. Of the surfaces. Let's say 4 surfaces. Mm-hmm. Yeah. Okay. Everybody happy? Maybe one thing I can say, this is probably familiar, you just put a very massive Wilson line. Here you do the same construction, so I'm in 7 dimensions. I have a 4 surface here, S4. I surround it by some 2 surface, and I'm declaring that the integral of the obstruction, which I'm going to call W2, for lifting the appropriate PSUN bundle. So this is often called PSUN. To SUN on these 2 surfaces is equal to 1. So that's my definition of this object.
Sorry, y equal to 1?
Well, sorry, yeah.
What you want to measure?
Yeah, sorry. My conventions is equal to 1 mod n. And this thing is a class in H2 of my manifold with Seden coefficients. It's quite common also, yeah, to put this as a 1 over n class and do this mod 1. Yeah. Okay. There's an additional symmetry. It's a continuous 2-form symmetry. Generated by the integral of f which f. It's a trace, I guess. Known as instanton symmetry. Okay, the background here will be gamma 3 with curvature d of gamma 3. And what this thing is measuring is in 7 dimensions you have configurations that look a bit like an instanton if you measure them from a transverse space but behave dynamically. Perhaps a more familiar example in lower dimensions would be a monopole. You say that you have the trace of f around the monopole, but this is a dynamical particle. Okay, the last thing that I would like to reproduce from the field theory here is that in the SUN global form, there's an anomaly, mixed anomaly, which is of the form of gamma 3 cap. So I'm going to call n inst of B2, which is the fractional instanton number in a B2 background. So that's defined modulo 1, but this is an integral class, so the modulo 1 does not affect my anomaly. It's only the fractional part of the instanton that matters. Okay. So let me explain why this arises, and then I'll explain what the formulas are, at least in SUN. So putting a B2 background in such a theory, in SUN theory, in terms of the path integral, amounts to imposing that W2 of your bundle is equal to B in the sum over topologies. That is the path integral of an SUN theory with a B2 background is going to be a sum over those bundles of PSUN such that W2 of E is equal to B. The standard prescription, I mentioned before, this was the abstraction for lifting PSUN bundles to SUN. If I don't put a background, that means that I can lift all my bundles to SUN, so I'm summing over SUN bundles. But if I put a background, I'm summing over specific PSUN bundles. Then don't admit a lift, but the way they don't admit a lift is restricted.
I'm sorry. Isn't there also an obstruction on 4 cycles?
Obstruction on 4 cycles?
Yeah, like on 2 cycles, W2 is an obstruction, right?
Yeah.
I agree. But let's say you have S4. There are PSUN bundles which are not SUN bundles, where trace F wedge F is a fraction. So I think there is an obstruction on 4 cycles, so I don't understand.
Yes, there's going to be my fractional instanton number.
Yeah, so I think that's not the only obstruction.
Is that one W2 squared or something like that?
Yeah, that's what I meant to.
Yeah, it's W2 squared, I think. It's homologous to W2 squared.
Yeah, so I'm not going to put a
But it's
restriction.
not really W2 squared, because even if there are not 2 cycles,
Yeah.
there is an obstruction.
Well, I'm not sure I would call that an abstraction. I would say that you sum over all bundles that satisfy this, and some of those will have fractional instanton number.
Okay.
And that's a property of those bundles. The fact they have fractional instanton numbers is the fact that they're going to be charged under this U1 instanton transformation. So that's the origin of the anomaly. In those cases where a fraction is not a number, I have a charge under this U1, and my partition function is charged, so it's anomalous. Yeah, but I don't want to restrict in that way. I don't want to say my fraction is not a number is 0 or anything like that. That I don't want. I think that yeah. Any other questions?
You're not going to be interested in the zero form symmetry obtained by trace of Q?
Trace of Q. Sorry, what's Q?
So yeah, think about trace F squared, right?
Yeah.
What about trace F cubed? You're not going to be interested in that?
Oh, yeah. I could think of that. Yeah, I'm not going to think of it. Yeah. Yeah, good point. Yeah. I haven't done the exercise. I don't know. Yeah, I think there was a question back there. The same question. All right. Yeah. So the answer is I'm not going to talk about it. All right. All right. So as Sohar was saying, there's a relation between n inst of B2. So the fraction is not a number, and B2. In cases without torsion, you have that n inst of B2 is n minus 1 over 2n times the integral of the square of B2, which B2, sorry, it's integral. More generally, n inst of B2 is n minus 1 over 2n, the Pontryagin square of B2. So I'm not going to need to define the Pontryagin square. I'm going to restrict myself to cases in which I don't have torsion in my manifold, in my 7-dimensional manifold or 8-dimensional manifold, in which case I can think of the Pontryagin square as an actual square. Okay. So those are the things I want to understand from the string theory construction.
Are you writing down the equation? So you start.
No. 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 So then what I would have to do is to do the path integral over connections on this bundle. And the fields in n equal to 1, Yamil's theory in 7 dimensions. So those are going to be some gauge genons and some scalars. And then I have e to the minus s Yamils of these fields. A, E, lambda, phi. Okay, so those are the things I want to reproduce from some string theory construction. And the next thing I have to tell you are what's the string theory construction, what are the rules for understanding those things. So let me start with the string theory construction. So I'm going to use M theory on a space of this form, so 2 times M7. So if I want to understand this n equal to 1 theory in 7 dimensions on some 7 manifold, the thing I can use is M theory on this specific space, which is singular. times M7. So the interesting things will happen in here. Right? The field theory lives here, but all that data comes from the geometry of this orbifolding here. So, oops, sorry, it should be set N. All right, so I'm going to parameterize set 2 by some coordinates, x and y, and set N acts on these ones, x and y, by omega n x, omega n minus 1 y, with omega n the nth root of unity, so this space is singular at the origin. And the field theory will live on this singularity. So here's the cartoon. I have C2 mod set N here, times some M7. There's M7. M theory, whenever it encounters a singularity of this type, generates degrees of freedom which are localized here, which give me n equal to 1, d equal to 7 superjammers. So notice that this has 4 transverse dimensions. And, oh, sorry. Does anybody not know what M theory is? That's how I was teaching. That was not very pedagogical of me, I apologize. Thank you. All right, so M theory is...
You have 3 minutes to explain M theory.
Okay, I'm going to fail. Yeah, so as in much of what I'm describing so far, I'm going to think of the low energy limit of M theory. We don't know actually what M theory is. So I've been assigned an impossible task here. But at low energies, this becomes an 11-dimensional supergravity. So in this case, in 11 dimensions, there's only one choice for the supergravity. It doesn't have particles with a spin bigger than 2. So when I say supergravity, this is uniquely defined. With the following field content, which again is determined by supersymmetry. So what do you have? You have the metric. You have a gravitino. And you have an antisymmetric 3-form field. See. So the field content is very easy here. We really just have the gravitino. The action involves, so you have the standard actions for all these fields in supergravity, but there's a funny coupling. Okay, these are going to be sort of the most important ones in my story. The first one has this form, -1/6, C3 wedge G4 wedge G4, where G4 is dC3. So here C3 is this one here, this field here. And there's another coupling, which is of the form C3 wedge X8, where X8 is a polynomial in P1 and P2. Okay, so for analyzing the system, this is all I need to understand about M theory. The fact that it gives rise to some localized degrees of freedom with algebra SUN. in this particular orbifold, and that there are some Chern-Simons couplings in the action. From these two ingredients, I will be able to reproduce all those facts about field theory in the next lecture. Thank you. Thank you. That's all. Yeah, a question.
X8 comes from anomaly cancellation in 11 Suda.
Yeah, this interplays with anomaly cancellation in M5 and things like that. Yeah. There's many reasons it has to be there. All right, thank you.